So these are the global earthquakes. Probably time updated this 2006 to 2011. Pretty interesting. So first question is, where do earthquakes happen? Hopefully you can identify where these earthquakes are happening. If you said plate boundaries, you would be correct. Why might they occur in these places? If you said it's because there are two bits of crust moving independently of each other, but they are touching and they get caught up together, build up pressure, and then have to rebound. If you said something like that, maybe you didn't say exactly that, but if you said something like that, you'd be right. Where did the largest earthquakes occur 2006 to 2011? This is leading into a particular event. So if you determined that it was up here and you know that underneath there is Japan, there were some massive earthquakes in 2011 causing a huge tsunami. You may have seen stuff, but it was a fair while ago. If you were too young to remember it, I will forgive you. But it was pretty significant, and there was a lot of damage to Japan, particularly they had problems with a nuclear power plant at Fukushima. A fair bit of radioactive stuff ended up places where it shouldn't be. So usually occur at tectonic plate boundaries. You can have some intraplate, so that's within plates. So large earthquake, we'll look at this in a second, large earthquakes happen mostly at converging and transform plate boundaries. You can see when they're moving apart, it's not going to cause too much. So earthquakes that happen deep in the mantle, when the mantle is mixing around, they'd be pretty strong ones, but we don't feel them at the surface. They run out of energy before they get to us. So let's have a look at this little one. All right. So it's from Geoscience Australia. So we've got the layers of the Earth. That looks like a subduction zone. So we have the oceanic crust subducting under that. Looks like oceanic crust as well. We can see that it's buckling, building up pressure, and then it releases. When it releases, it sends energy upwards through the ocean, and we get a tsunami. Thank you, Geoscience Australia. So subduction zones, like we just saw, this one's continental oceanic collision. So we have the oceanic subducting underneath. We can see that the X's mark shallow earthquakes. So we're certainly going to get them where there's contact between the plates. We can see we get some deeper ones further down. The deeper you go, the less they are felt at the surface. So there's a little bit at the surface at subduction zones when you have those big earthquakes there. There tends to be a lot of force involved in these. So they can cause a lot of problems even though they're relatively deep. If you have earthquakes at really shallow areas, so they don't need to be as powerful in order to get damage at the surface. They also occur at transform boundaries, and here we have, you may or may not be able to recognise, it might have taken you a second. We have the continent of Zealandia, and then we have New Zealand in the middle. Now, really interesting spot, New Zealand. Very tectonically active, a lot of volcanoes, and a lot of earthquakes, particularly relative to Australia. So we have a plate boundary coming through here, and you'll notice that the plate boundary actually goes through the South Island of New Zealand. The North Island and the northwestern parts of the South Island are actually Australian crust. So they were there when New Zealand broke away from Australia. It's Pacific crust down here on the easternmost part of the South Island. Up to the north, we have the Pacific plate subducting under the Australian plate. So it's going under here. But unfortunately for New Zealand, or maybe fortunately, because, you know, volcanism is actually pretty good when it's been happening for a while because it brings really great soil, which can form essentially because basalt, obsidian, they don't have big chunky minerals like granite. So when you weather granite, you're going to get sand, silicon dioxide, so quartz. But when obsidian weathers, it's weathering into almost elements because they're not in crystals, or they're very, very small, and in basalt as well. So when that does, and it takes a long time, but when that does become soil, or break down and add to the soil, the nutrients are really available for plants. So you get a lot of productivity in areas that were previously volcanic. Because these aren't going straight towards each other, we actually get movement in the New Zealand South Island. And it's called the Alpine Fault. New Zealand is very young crust, so 500 million years old. Formed at a plate boundary between the Australian Pacific plates. There's also a hotspot under the North Island of New Zealand. So there's not just subduction related volcanoes, there's also a hotspot. We can almost see the Alpine Fault running through here. Pretty cool. So because there's different soil types coming from different types of crust, we're going to get different plants growing on either side. You know, probably not greatly different, but a little bit different. This could also be due to weather. So there may be a wind coming up from the west in New Zealand, which doesn't allow snow. And then we've got the mountain, and then on the other side of the mountain, it's more protected so snow can settle. So hard to say which one. Probably the second one. I don't know. And we can see that movement there. So with high mountains and frequent earthquakes, very geologically active. These are all of the volcanoes in New Zealand. Mount Horrible. That's a pretty good name. Wonder why they called it that. Must be terrible. So White Island, I think, was where they had the volcanic eruption last year that caused the deaths of numerous people. Okay, here we can see the subduction zones. Remembering that when you've got the line with the little arrows on it, that tells you the direction of the subduction. So the Pacific plate here is subducting underneath. Here we go, volcanic zone through here, which again is probably around 100 kilometers in, which is often where you'll find those volcanoes. So we've got subduction going underneath to the south, and then we've got the transform coming through the middle. We've got some other little transforming here, like in Iceland. It's never going to be perfect. It's going to fracture along a few different ways. California on the west coast is famous for the San Andreas Fault. Going through. This is pretty interesting. They've got it on right on the fault line. So you got to be pretty clever to work out where to put that. I guess if you didn't put in the right spot, wouldn't be worth a photo, so we don't know about those. So we can see these were once circular shapes. And we can see that there is some movement there. Hard to say how much it is. That could just be a few centimeters. So a seismogram is the graph of an earthquake, and they often look like this. The machine that takes it is going to look like that. Geez, that's a massive scribble there. There's a few. That looks like an earthquake somewhere, doesn't it? Just in this little spot here. There are a number of waves that we get. So we get a P wave, an S wave, and a surface wave. We can see which ones do the most damage, and they're the surface waves. But P waves and S waves. So primary, secondary, let's get to that on the next slide. So primary waves are longitudinal waves, so they move back and forth. So we got a primary wave back and forth here. We got a separation, then a contraction. If we've done physics already, you'll have a good idea of what a longitudinal wave is. It's sometimes called a compression wave as well. So particles just move back and forth in a spot, and the energy is moved to the right or left, depending on which way it's going. Secondary waves, they move in a different way. So as the secondary wave comes through, the particles really maintain their position, but they move up and down. They don't move in the same direction as the energy. So up, down, and it passes the energy along. And we can see that the energy is going that way. The thing about primary waves is they can move through solids and liquids. These are like a sound wave. But secondary waves can only move through solids. That's of use, the fact that we've got two different types of wave and we know some of their properties. Surface waves are the slowest, but they cause the most destruction. Oh, P waves are the fastest. We have a diagram here of the S wave pattern. Now we can see that the epicenter of the earthquake is here, so that's where it's generated. We can see something interesting that's going on here. Hopefully you can identify that. So the S wave does not move through the outer core. Why not? If you said it's because the outer core is made of liquid and S waves can't move through liquid, well done. We've got a P wave over here, again the epicenter, and we notice that we've got a similar shape to the S waves because they're refracting. So they're not going in straight lines because they're refracting to do with different densities of the rocks in Earth, so relating to different temperatures and different pressure. So we're going to get refraction there, and if you've done physics, you'll understand that concept. So when it gets to the outer core, these compression waves can still pass through it. We're getting some refraction as well, so it's a change in direction to do with density differences, and then they're going to come through to the other side. So earthquakes also tell us a lot about how the Earth is made, what it's made of. To get this sort of behavior from these different types of waves, the outer core must be liquid. So here's some wave velocities. This is what I was talking about before, about different densities or different properties of material. So dry sand, waves don't go very fast. P waves or S waves. We've got some varying degrees. So the waves are going to travel, not all sand is exactly the same. So clays as well. So we notice P waves are the fastest in all of them. And we also notice that S waves are the slowest. But as we move down, we get to granite and basalt, we can see that the waves are going faster. And that's because these are more competent, basalt and granite. So they're stuck together a lot better, there's less gaps, they're also very, very solid. A brittle rock, whereas the ones down here are a bit more plastic, like wet sand or till. Mudstone's quite flexible. Sandstone, grey, very, very big degree of difference in speeds in sandstone. That's because sandstone is essentially just sand that's cemented together, and I guess depending on your cement, or depending on how much it's being compacted, that'll have a big impact on how fast things can move through, or the density and how fast things can move through. So we can see the velocities here, similar to the last one. S waves, and bang, they stop when they get to the outer core. P waves go through them, solid, 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 then we get this massive drop in speed because they're going to move through a liquid. And the particles in a liquid aren't as close together, they're not as dense. And then we get to the inner core, big jump straight back up. This is a tomographic profile of an area, so it's kind of like a bit of the Earth that's been cut into. And then we're looking at it from side on the surface is up here. We've got Tonga volcanoes and Fiji. We've got some volcanoes there. We can see that P waves are moving quite quickly through the blue and a little bit slowly through the red. So Tonga Arc, there's volcanoes, so this might be magma. So it could be liquid all through here. In fact, it probably is. What can you identify here? We've got the Pacific Plate up here. What does it look like? It looks like a subduction zone, doesn't it? Dense oceanic crust made of basalt. And it's subducting in this direction. That looks like the front of it. A lot of earthquakes as it's trying to push its way through the mantle. Reasonable amount of earthquakes associated with it, but particularly where it's trying to push its way in. That makes sense, doesn't it? Triangulation is a method that we use to identify the epicenter of an earthquake. So triangle, 3. So we need 3 different locations to find the epicenter. I'll explain what these circles are in a sec. P waves can be detected worldwide. S waves can't be, so anywhere where it's got to move through the outer core to get there, you're not going to pick it up. S and P waves go different speeds. So the bigger the gap in between when the P wave and the S wave arrives, the further away the earthquake is. If there's a small delay between when the P wave and the S wave arrive, we know that it's much closer to where the detector is. And we'll get to what we use that for in a sec. I'll put all of these videos in the description, or links to. So again, same stuff again. Station 1 here, Station 2 here, Station 3. So we notice that the time delay is less at Station 1, it's closer to the epicenter, and greatest at Station 3, it's further from the epicenter. We can see it in a different way here. So this is the seismograph. P wave arrives, S wave arrives, and we can see that that's a smaller gap, that's a bigger, and that's the biggest. And if we get, somewhere even further away, we may get a longer interval, but the waves would have to make sure they didn't pass through the core. If they pass through the core, you're going to lose the secondary wave. So again, we can see the same thing going here. Difference in time, we can see the curves move away from each other, indicating that this becomes greater. Okay, Station 1, Station 2, Station 3, we can notice big circles and a little circle here. So Station 1 is the closest, so it's got the least gap in time. So how do we calculate the distance from the epicenter? We've got locations, we know when the P wave arrived and the S wave arrived. We're just calling that 0. And then 60 seconds later it got to Catherine. 80 seconds later it got to Meekatharra, but 30 seconds after it got to Bairnsdale. So Bairnsdale's in Victoria, Meekatharra is in Western Australia, Catherine is in the Northern Territory, and Ceduna is in South Australia. Okay, so what we need to do is to work out the time difference, and then using this graph, we're going to work out how far. So time difference here is 90 seconds. So we go, this is time in seconds, so we go up to where 90 is, which is about there, and we move across and see where it hits this curve, and we come straight down, kind of, it's about there. So we can decide that that is about 850 to 900 kilometers away. So we put that distance there. Whoops, that's cheating. Anyway, it doesn't matter. So we've got Catherine at 212. And so we're going to come across here and we're going to look and we're going to go, it's just a bit over 2,100 kilometers. Meekatharra a little bit further away, 2,150, and Bairnsdale coming across at 120, it's going to hit there, and it's about 1,200 kilometers. How do we use those? Well, so we've got our distances here. At this point, these are the only things that are important. So we've got a little scale down the bottom. So that's 500, that's about 800 kilometers, is about 500 miles. So that distance is 800. So for Ceduna, we're just going a little bit further than that. So it's about that distance at Ceduna. Ceduna's here. So about that distance, we're going to have a circle around Ceduna, reflecting that 900 kilometer diameter of the circle. Then we go to Catherine, 2,100. That's going to be really big. It's going to be 2.5 to 3 times as big. So we're going to have a massive circle here. Meekatharra as well. We're going to have a massive circle around Meekatharra, which is here. And Bairnsdale, not as big, but still pretty big. Okay, that's what it looks like. It's got these circles. You only need 3, but there are 4 in this one. So we've got these big circles. Where do you think the epicenter of this earthquake is? Right there. Southwest Queensland. There's nothing there. Okay? Hopefully that makes sense. So causes of tsunamis. Unknown just means we don't know. It doesn't mean we don't know what caused them. It's one of these other ones. But we don't have enough information to determine what caused it. So subduction related earthquake and tsunami. We had a look at this already. So these are both oceanic crust. We can see there's buckling, because they're stuck together, and that can only last so long. We get an earthquake, pushes water upwards. Thanks, Geoscience Australia. Japan. Pretty interesting place when we're talking about earthquakes. Pacific, Philippine, Asian. Eurasian plates. This is not a very nice recipe. Philippines going under Asian, Pacific's going under Asian, and Philippine. Mariana Trench is somewhere down here. So we got some serious buckling going on here. So Japan, and there's also a plate boundary coming through here. Japan gets some significant earthquake activity. Lots of volcanoes. What's this a diagram of? Over here we have distances up to 120 centimeters starting at 0. Got the 120 here. 0 around here. Okay, 0 to the west of Australia. So here's Japan. It's the height of a tsunami. So the wave height. Makes sense. Highest waves coming straight from the source and then loses energy as it moves across the Pacific. You know, some of it comes around. New Guinea got a fair bit actually, but protected Australia. New Zealand got a little bit. Hawaii, we've got a reasonably significant amount. So they would have been on tsunami alert for sure. So people would have been moving away from the coast in order to stay safe. You can look up that one. Footage of the Japan tsunami. Some of it can be a bit disturbing because at times there's people dying and things like that. So Japan was pulled away from mainland China 15 million years ago. Let's not worry about slab rollback. Created a back arc basin called the Sea of Japan. And the Sea of Japan is between Japan and China. Japan used to be attached to China. Japan's earthquake and tsunami. So here it is. This was on one day. No, it wasn't. This was over a few days following the main earthquake in Japan. Magnitude 9.0. So it was happening over a few days, and that triggered that tsunami. Some of the damage, not insignificant. So in Boxing Day 2004, there was a tsunami in Indonesia, in Sumatra. Yes, you can look up that video if you want to as well. Some of the stuff that came out of Sumatra, some of those videos are quite disturbing. You see people who are definitely going to die. That's not nice. So this is where it happened. There we go. We can see that Bangladesh and India got smashed. Bangladesh absolutely got ruined by this one. I think 200,000 people, died in Bangladesh as a result. Often really poor people. And some of them would have died following because all the water comes in. You don't have natural water, you've got mosquitoes, you've got disease spreading, all of those sorts of things. The waves are up to 30 meters high. Isn't that insane? What are you going to do in those circumstances? Seriously. So, tsunami warning system. So, Geoscience Australia has stuff in New Guinea. That makes sense because New Guinea is getting hit by those earthquakes coming out of Japan. There's a little video about it. And that is all. Well done.